Hello YouTube viewers, welcome to my channel Science and Technology. In today's show, Science Thursday, we're going to talk about liquid tree. So let's dive deep into it. Now first, what exactly is the problem? Well, problem is city is heating up, and I mean everywhere, and it's getting more polluted. So it's a double whammy scenario. And be mindful, whenever we say the CO2, you have to understand that CO2 does have local concentration. As in, if you're talking a metropolitan city, everybody is burning their vehicle. It's not that that CO2 gets equilibrated instantaneously. It does stay there. It's almost like a heat island effect. All the heat will eventually radiate out, but it will become hotter in that local region. So same thing happens here. So not only carbon dioxide is becoming more, but pollution is also there. So why can't we just plant a tree? Here's the deal. Trees can't handle it. We have crossed this threshold like in 2008. Trees simply can't. And as temperatures are getting hotter and hotter, tree will simply burn. Like this is happening in Delhi and other places where it's like you have to pump a lot of water in trees, every tree, and then also they are barely holding on. So yeah, we reached a point where they are like, yeah, we exceeded their capability long ago. On top of that, even if you're like, you're spending money, you're planting the right tree and going YOLO on it, the CO2 sequestration speed is too slow. It's just too goddamn slow to have any impact. Even on a local region, I'm not even talking like global, local region is just too slow. Like fundamentally too slow, and we don't have enough space for it. Like it sounds good to say that, oh, let's just plant like all the trees. Yeah, where would you plant it? And it might sound very easy to bitch about these things, but you have to be realistic about it. It's like you look into the Central Park in New York, it's like, oh, it's a big green square. Zoom out a bit and watch a population heat map, and then you're like, oh, it's not enough. So fundamentally, we don't have enough space, and we have high density urban living. What can we do with that? Like tree will not solve it, but something in tree can solve it. So we need tree 2.0. Basically, we need something smaller and capable. Biology have the tool, we just need to scale it differently, so to say. So that's the problem. Fundamentally, we have reached a point where trees can't help. We don't have enough area to do that. And while it sounds very easy, oh, just destroy all the buildings and put tree, who will pay for your house? Because you won't be able to afford any house after that. And right now people are complaining. Yeah. So it's one of those things that sounds very good and mighty to bitch about, but you have to be reasonable. Like bitching is good, but like it does not get job done. I like to get job done. So photosynthesis, that is the tool that will solve us. So what is photosynthesis? Is the OG solar power. Now be mindful, what solar power we use is basically photons into electron conversion. It's efficient, it does work, but it's not chemical. OG solar, as in photosynthesis, that puppy takes basically stuff in air and converts it into chemical energy. Basically, it makes liquid fuel out of it, fundamentally. So you take carbon dioxide, I'm reasonably sure all of you have studied this in school, add water to it, cook it with photosynthesis, as in solar light energy, voila, you get sugar and you get reject oxygen. So oxygen is the byproduct in this. So we can live with that. We can live with that penalty. So, and the fuel, the glucose here, can be used to make structures also. Not only it will fuel the plant itself, but it will also build structure, as in there is other enzymes, other engine that will consume this and make stuff. What stuff? Something like lipid. Like if you look into lipid structure, it's just hydrocarbon. It's literally long chains of hydrocarbon, and that's why I keep saying that it's super duper easy to make a diesel, biodiesel specifically, from algae or seaweed, simply because the lipid content is very high. What does that mean? That simply means break this glycerol chain, D, and you get a diesel. Like flat out, you get diesel chain. And again, that's a college level experiment people do. It's like we have been doing this, we know this works. So if you take a tree, no matter how old or how big or behemoth it is, let's say it's a 100-ton tree, you kaput it, like you Dr. Manhattan it into its elemental breakdown. I do not mean compound, elemental breakdown. You'll find mostly it's made out of two things, basically carbon and oxygen. While it does have a lot of hydrogen, hydrogen is very lightweight. So in mass ratio, you will see these three elements as the daddy, as in carbon, oxygen, hydrogen. And then you will see some trace amount of nitrogen, even smaller trace amount of sulfur and other stuff. So fundamentally, that's the reason when you plant a tree, your soil does not disappear. It's not running on soil, it's literally running on air, as in carbon that it eats from the basically carbon dioxide and hydrogen that it leaches from the water. It's basically running a sort of electrolysis. So that's how you get a system that consumes water and gives you everything that you want, specifically glucose. Now, Water is the only payable because again, you are not taxed for the sunlight and you are not taxed for the carbon dioxide. People want to consume carbon dioxide some way. So carbon dioxide is free, sunlight is free, water. Now, algae is one of the most efficient system on the planet, flat out. If you have a limited surface area, let's just say 1 square meter, how much glucose you can make will fundamentally be better in a algae compared to anything else. The second best would be seaweed, and then after very long drop down, you will find things that are growing on land. Why? Gravity. When you are growing in liquid like seaweed, you are floating. You're not fighting gravity. So that allows you to salvage the glucose into lipids. So you can have higher lipid content. If you are on ground, you have to fight the gravity to grow up. That means you have to convert most of it into cellulose. So yeah, that makes it difficult. Again, not impossible. It's at the end of the day still hydrocarbon. That's why we used to convert basically wood into charcoal. But again, extra long process. This liquid fuel. And again, algae is even better because it's a singular cellular structure. That's all it has is lipid. So lipid content on this is lipid only, relatively speaking, compared to plants. And this is the photon absorption spectrum of it. That's why you will keep hearing the word of blue-green algae. That's the whole point of it. So that's how it was. The original photosynthesis, basically solar energy that converts a waste product, carbon dioxide, with little bit of a precious product, which is water, and voila, you get basically hydrocarbon out of it. And that hydrocarbon, once you burn, it releases everything again that is consumed by the next cycle. It's carbon neutral, meaning if you use this system to drive your systems, there is no extra carbon dioxide. It's not like fossil fuel where you are redumping carbon dioxide that nature removed it. It's cycling. And what is the energy source? Sunlight, tax-free. So this is what we want. Photosynthesis. Photosynthesis is a real thing. It works. It's known, in time tested. We good. This is what we want. And the best agent for it is algae. The smallest, the most fastest, the most rapid. Meaning in few days, this puppy will start to compete with a 10-year-old tree. And in a month, it would have surpassed a 10-year-old tree. Now that takes care of the carbon dioxide part of it. But what about pollution? Here's the sending air through basically a bubbler kind of structure, like how you have a fish aquarium. Algae water acts like a pollutant filtration and bioremediation. This is the critical part. There are a lot of ways of filtering air. One is you just send it through the filter. It removes it. Okay, but then that becomes your hassle. It's like, okay, now we have this mess. What to do with that? Second option in some scenarios is like, what if you break it? For example, your catalytic converter in your vehicle is designed very specifically so it takes NOx, breaks it, and gives you oxygen and nitrogen. Harmless. That's what we want. That's the end game. To not have, oh, we have this mess. No. Convert the mess into a good, useful thing. Bioremediation done by algae because of the surface area and because of the chemistry. Some of the pollutants that we have, like major components of the pollutant, is spicy food nutrition for algae. Like algae will say, hey, this is spicy food, Indian food, but it can eat it. What does that mean? That simply means VOC, volatile organic compounds, NOx, SOx, SOx, these are spicy food. It's just like directly eats it. As in, NOx will go into nitrate and nitrites forums, as in like from algae point of view, it will be converted into proteins. And sulfur, it will become ammonia acids and all cell walls. And basically, it will be dissolved, broken into other structures. It will not be like, oh, it's just now this has it. No, it will be broken into useful, safer position. And then you have VOCs, which generally becomes into lipids and fats. So fundamentally, this is bioremediation. You're solving the problem. So let's just say you have a road that has a lot of vehicles going through it and you have these on the sides of it. These things will be happy. It's like, hey, we are getting spicy food. And again, evolution and selective breeding will help it to optimize only for that extraction. And voila, it's not just like, oh, we have the mess. It's like it will remove it. Now, another thing that is a mess, it will remove heavy metal from air. For example, let's just say you have mercury or lead or uranium. It will remove them. That's the good part. Bad part is it just removed them, as in it moved them from the air into this biomass, and that creates a hassle. For example, let's just say most times it's not a big deal, but what if you are in an industrial place where you have heavy metal contamination, as in air, you want this to remove it from the air. That's great. It's just that now you have limitation what to do with biomass, because that biomass, while it has taken care of, like, bioremediation of VOX and NOx and SOx, great. It does not do anything to lead in the air, so to say. So that becomes an issue. Basically, if you are like, hey, I want to use that algae to make a food supplement, people will remind you that please make sure you do not have heavy metal in the air. If it has heavy metal, again, some amount of ppm is acceptable, but like generally it has to be like in bpm, parts per billion. So that is a minor issue. I have not seen any bioremediation for heavy metal, only heard that there are some fungus and some specific type of what you call mushrooms that can soak those up, meaning in principle maybe in future you can have something like this and you send the bio waste biomass of this into a cooking pot, and in that pot you grow mushrooms. Mushroom leaches all the heavy metals out of it. So basically parts per million that could be 100 can drop down to, let's say, a safe level, let's say 1 parts per billion. At that point in time it's usable. Again, not sorted yet, but these things are sorted. So it will, from a city point of view, whatever city you are talking about, it will clean the air, very large portion of it. Like majority of the pollution is not heavy metal, it is VOx and NOx and SOx. So cleaning those things is shut up, take money. And it is cleaning them, let that be very clear. It's bioremediation. And yes, plants also do that, but very slow. Like slow. And again, bigger plants generally do it on root level. So yeah, not that fast. Flat out, not fast enough. Algae, I got you, fam. That is the biggest like night and day difference that you can do. And again, parts per million, it's literally going through a liquid filter. So ppm counts also goes down in air. Now we talk about the management. So those parts are the good part. How do you achieve those good parts? Well, it does need water. Let that be very clear. Water is the primary consumable here, meaning, oh, I saw a tank, it will be the tank. No, the water will keep evaporating. It will keep being converted into biomass. You have to keep replenishing, as in water is consumable. But if your target is, I want CO2 reduction, the amount of water you will consume per kilogram, it's exponentially better than any tree known to humanity. So it's not even a conversation. It's like, yeah, if I want CO2 reduction, burning that water via tree versus burning that water via algae, it's not even a discussion. It's like not even 10-fold, it's 1,000-fold. That's how big of a difference is there. So there is no discussion there. Yes, it will consume water, but it's a healthy water consumption, as in like more work done. Second, it can double every day, as in 24 hours, boom, you put 100 gram, it becomes 200 gram. That is real world speed, by the way. So it can achieve that. However, it will slow down very drastically because it will run out of macronutrients. And again, this is why we want that sort of what you call starvation, because we want to reward the algae mutations that specifically eats that spicy food. So macronutrition, and assume that it evolved that, right? You did that in 5-6 and again, that's why we already know certain strands that are like, bro, VOCs is my jam. Certain strands is like, bro, NOx, I can directly digest NOx. So we have that right now. But if you have that, you will hit the final constraint, that is space constraint, meaning if there is 10% algae in water, the shading on the core parts of the algae, it's not that much, meaning sunlight is penetrating a lot. And again, the something that is in center, it's really like, it's not eating, gorging itself, but it's like, bro, I'm good, I'm gonna do it again. I will slowly mitosis, but I will do it. But if you have 20%, ooh, yeah, 50%, nah. So it will reach a what we call spatial constraint, meaning your tank will work. And that's why we generally do not want tanks, we want thin walls. So sunlight has enough what you call not self-shading. You want enough lights to, almost like a solar panel. You do not want solar panel to be shaded. Same thing happens here. So slim, long walls are much better compared to like, okay, big tank. Big tank, because inherently at some point it will become a very concentrated on the surface and volume would be useless. So basically evaporation and biomass conversion would be the primary system. And ideally you want maximum biomass conversion, minimum evaporation. So, but again, given the constraint, if you have water constraint and you want to do maximum work, it's not even a discussion. Again, you will work on optimizing the geometry, but it is doable. Now, biomass does need to be harvested regularly, meaning this becomes a hassle that you have to deal with. Like tree, plant, water, and forget about it. Here, it's like you have to go and flush this puppy out, as in like extract all the seaweed out of it or algae out of it. Like you can make jet fuel out of it. It's not recommended, but you can do it. It's like, why would you do that? Because what's the use? So, but you have to figure out a way. Like that's the hassle part. Water is not that big of a hassle. Bubblers, not that hassle. And again, that's why you will see a lot of these systems have solar panels. They are maintaining the system, as in they are figuring out what is the pH level. They are figuring out what is the air concentration into those systems. And again, that gives them the feedback, is algae healthy or reached saturation. Once it's reached saturation, you have to extract it. How do you do that? What do you do with that? That's up to you. There are a lot of options, but I have like again, it's not done on large enough scale where people have a sorted solution for it. It's like we can do this, we can do that. It's like, what is the least headache option? I would say convert it into biochar, because that solves the problem of heavy metal. Where's the least harmful place to put heavy metal? On the ground. We literally mined it from there, might as well bury it there. So that is there. So be mindful, that will be very clear. If you have heavy metal contamination in the air, it will remove it, but you cannot use it as food supplement for humans afterwards. So it does require certain level of management. It's not like put and forget. Water wise you can do that, but you would require some way of flushing these things. So what can we expect in the future? Well, here's the deal. It's a good tool for high density urbanization. When you have something like that, yeah, it's not gonna be helped by trees and all that. It sounds good. It sounds, you know, hassly and all that. It's like, oh, we're gonna do this. And it's like, yeah, it's not enough. It's flat out. It's not enough. So, and bioremediation solves the problem. That's the critical aspect. A plant will not do that. Again, even if it does that, it's so slow, so minuscule, it's irrelevant. But bio is like, bro, I can digest it. That's my job. I can digest it. So it solves major part of air pollution. Like, what is air pollution? It's those things, NOx, SOx, and VOCs. So solving that is a very big thing. And it beats tree exponentially. It's not a little bit better, it's exponentially better. But it does need support system. That's why it's not like, oh, why haven't everybody done it? Like, first, it has to be bad enough for people to try. And second, it does require certain, for example, liquid 3. I'm pretty sure they made it liquid 3 because somebody already had patent of liquid 3. So they're like, okay, liquid 3. They said like they have to flush the tanks every month, so to say. Again, it could be automated system. You go there, you plonk a pipe to it, cycle it, done. So it could be automated. I could easily see that. Like, you know, same way you have garbage truck. So one truck, again, brick by brick, doing it day by day, because again, let's say a big truck can flush 50 of these. You can easily do that in, like, you know, one after the another and all that. And by the time you do the last one, you will first one will reach the point, and you do not need multiple trucks. So there is a what you call requirement of solving it. Air pumps, again, we have enough aquarium technology that we got this. Like this sort of structure you want. This is in India, this is in Europe, where you can say like it's a slim wall structure. The design is specifically for that. You want maximum photon and minimum self shading. So that's the whole point. So water lines that it requires is easy. Biomass extraction, that's messy but doable. Again, we know how to do it. So, and there are a few players like liquid 3 is already there, liquid tree in India is already there, and few more have already entered the market. So it is a useful tool for a specific requirement. Meaning, would I see this in farmlands? It does not make sense. Would I see this in next to basically industrial area? It should be mandatory. It's like, because again, you clear the air at the source, problem almost goes away overnight. So having this is a really good solution there. And again, cleaning the air of a city, actually solving it, as in bioremediating it, it's like cool. And again, we are not inventing technology for it. We are just like harvesting it. It's like, hey, sunlight, free. Photosynthesis, free technology. So, and I have a feeling after doing thousands of these, we will reach a point where we have special spicy algae that are very good at eating the vehicle exhaust. Because again, those will survive the best, because again, you are bubbling the air, and if you have car exhaust, those exhausts are going through it. So which one will survive the most? The one that can digest the most. So over time, thousands of cycles of it, which translates to like 3-4 years, I could easily see, oh, earlier we had algae that could only reduce NOx by, let's say, 3%. Now we have algae that reduces it by 75%. So again, it's a very good long-term solution of this sort of system, and does not require too much magical technologies. Glass, and people have talked about the physical positive impact. It's not green color, it's not green paint, it's organic green, which our eyes like. Our eyes are highest sensitivity in green spectrum. So having this sort of organic green is psychologically also very calming for people. And again, space requirement is negligible. Water requirement is minuscule compared to a plant, and the cleaning effect is exponentially better. Meaning people will notice it, like, hey, let's just say a giant area or a road central bridge is just like converted into this. And they even had the idea, it's like, hey, why these algae are not working at night? We don't have sunlight. It's like, we have street lamps. What if we put lamps in it? So people are seeing the green light and they have enough white bleed, but algae starts to work. Voila. It's not as effective as sunlight, but again, you were gonna light the road anyway. Might as well do double duty. So it is a unique approach and solving the problem. I like the title. Like, okay, there's a problem. Okay, what can we do to solve it? Not bitching, solving it. And none of this technology of it is like exotic or expensive. It's like, technically you can do that. Like, you can do that in your house if you want to. It's just that buying the right strain of algae might be messy. Other than that, nothing else is messy. And what the hell are you going to do after the biotreatment? You can bury it in the soil. That's also an option. So this was my presentation on basically liquid tree. I hope you have liked it, learned from it. In that case, please click the like button. If you have enjoyed it, please click the hype button. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.